bergabung dalam acara webinar kami hari ini. Dan untuk hari ini kita akan diskusi sharing mengenai precision laser shaft alignment, dan nanti ada studi kasus ya mengenai vertical shaft alignment. Dan bersama kami turut hadir dan bergabung prinsipal kami dari Easy Laser, yaitu Mr. Sven Fleiser selaku Area Sales Manager Asia Pasifik untuk Easy Laser dengan base di Singapura. Hi Sven, thank you. Hello, for Mr. us. How are you?
Thank you so much, well, and thank you and your team from PT Tiara to arrange this web event. I'm very well and hope that everyone who's joining today has a good day so far.
Yes, so we will start soon, and I will inform some information to the participant. Oke, Bapak Ibu, kita akan sebentar lagi mulai sharing ya dari Mr. Sven. Dan sebelum sharing, Bapak Ibu bisa melihat di chatting ada informasi dari tim kami, yaitu nanti jika ada pertanyaan silakan langsung ditanyakan melalui chat, dan nanti ada giveaway ya bagi pertanyaan-pertanyaan yang akan diundi ya. Jadi silakan diberikan pertanyaannya mengenai chat melalui chatting selama presentasi dari Mr. Sven. Dan juga nanti ada juga ada feedback untuk diisi. Nanti juga akan ada giveaway dari tim kami dari PT Tiara, dan mudah-mudahan lumayan ya untuk membeli takjil ya. Oke. Langsung aja kita mulai. Mr. Sven, we can start now. Please, your turn.
Thank you so much, Mr. Rajeki. Before going into the presentation and also introduce myself, maybe it's worth to say that, yes, this presentation is in English. I'm so sorry that I do not speak Indonesian language, but I hope you can cope with me in the English language, and you always have later on, of course, the opportunity to approach the team of PT Tiara that potentially can, come down to your site to give you a visit, to explain the details in then also your native language. So welcome everyone in that web meeting organized by PT Tiara about laser shaft alignment, specifically a little bit more to the end, an example for vertical alignment, but I like to keep it a little bit broad and speak about various things that are of concern when it comes to the machine in regards of reliability. What are the benefits? What are the reasons actually that maintenance departments, engineers like you and I, looking into the behavior of the machine to be placed in a trouble-free operating condition, to once increase the lifetime, but also second to reduce unplanned downtime or trouble with the problem, because that's what we are in the bottom line are all interested in, to be reliable, to be depend on the availability of the machine. Good. So welcome again to everyone. I go into the presentation. We talk about precision through laser shaft alignment. Just a few facts about Easy Laser first, who we are. So a couple of slides, if you bear with me. Easy Laser is a company in Mölndal in Sweden. So that's a town close to Gothenburg, the second largest city in Sweden. We were founded in '94, so we have a 30th anniversary. Still sounds very young, just 30 years old, but the technology in regards of using laser and throughout the electronics in precision way to align machine is not that old. That started about 35, 40 years ago when first technologies arrived on the market. And we as Easy Laser concentrate on developing solution, design, and research. We produce measurement electronics, so instruments and systems that help engineers all over the world to assess a machine in regards of the machine's alignment condition and also do the correction. So therefore, we are in our headquarters in Sweden, actually not that big. We have 80, 85, around 90 almost employees in Sweden. And all of those people, very smart people, smarter than I am, doing the research, programming. So today is a lot about coding and software in the apps that we have implemented in our instruments besides the hardware. But maybe worth to mention that the distribution worldwide of our solution into the market towards the end user is done through distributor, so partnerships that we have all over the world. And we're covering here about 70 plus countries that are covered. And we're having them here a little bit displayed on the map. So first, the headquarters in Sweden. We have an operation in Germany. I'm also German. I'm having a Swedish name, Sven, and working for a Swedish company, which is Easy Laser. But I'm based in Singapore, so a little bit complicated. But I'm now in Singapore 14 years, quite long, and have throughout my career shifted to area sales management, taking care of the Asia Pacific region and supporting distributor like the company Tiara, which obviously distributes and takes care of the Indonesian market. So I'm by trade an engineer, an electronic engineer, and an electric engineer. I studied engineering a long time ago in Germany, and have done many various services all over the world. Before switching to more the sales side, I'm consulting. I have given various kind of trainings in my past when it comes to reliability improvement, more related than to the vibration, but also to corrective measures. If you think about balancing of machine, alignment of machine, so there are a lot of topics that I have taken care in my past. And my past means I'm in this field of reliability, machine improvement as a machine doctor and laser alignment for more than 27 years by now. So besides headquarters Sweden, our sales operations in Germany and the support office in Singapore, the main distribution is done through distributor here marked on this map in yellow. So that's where we are represented by domestic and local companies like Tiara. You see on this map as well those blue drops, which are locations of service centers. Service means for us that's established service centers at mostly the distributors' offices and facilities who take care of calibration and repair of the electronics. So these instruments which measure up to thousandths of a millimeter accuracy typically need to be calibrated in a 2-year cycle. That's what we as a manufacturer recommend. And then the end customer have on all of those service centers the opportunity to engage for this kind of service. And our representative, just to repeat, is in Indonesia, the company Tiara. Located in Jakarta, we could say crossing and their customer relationship whole Indonesia, but also having a focus strongly on Sumatra when it comes to the distribution of Easy Laser. But we as a brand aiming for us and also promise to our customer is 3 main points. User friendliness that we implement in the app guide of the measurement instruments today. Then we are adaptable. That means the app, we have only one app called XT Alignment app. allows user today not only to do shaft alignment vertical and horizontal, they can with the same app also tackle balancing, belt alignment of machines, doing some vibration. And the latest we have actually launched last week is the approach towards the geometric. So we already could do flatness and levelness, everything about larger machines or the foundations of the machine. And the latest one is that we have now enabled the instrument to be able to measure bore. Bore means the center, a line of a turbine, of an engine block on its stern tube and things like that. And all of those features are available in one app that everybody of you can right now download from the app, find in the iOS App Store or in the Android store. So it's working for both platforms. And there's no password, no licensing. You just pair the Bluetooth components, the measurement units with the app, and then you are ready to go. Point 3 is that we promise and aim to our customer to be always precise and very reliable. Reliable in regards of our measurement instruments. So we have users in the market that using products more than 20 years. So that's obviously a generation of instruments that's rather old and still function. But when it comes to the usability of those instruments today, the most people prefer app-based, touchscreen, and automatically guided through the menus. So we have made in long progression through the electronics today, throughout also cloud connectivity and interaction of electronics together with data. So we as Easy Laser company typically differentiate products into different groups. That is shaft alignment and everything here included, like for example, also the soft foot measurement. Then we have belt alignment, some components, and geometrics. Geometric measurement could mean parallelism, flatness, levelness, bore as already mentioned, or parallelism. So everything parallelism connected also to squareness and perpendicularity. There are many applications in the machine where we using laser instruments and consequently the accuracy that comes along with it to measure certain planes to each other in favor of putting machines in the right position where they are supposed to be. A little bit more later on this presentation. Typical areas, and we had an exhibition here in Singapore last week. It was the Marine Pacific, the Asia Pacific Maritime APM exhibition, and many people came and engaged with us because we concentrating also with solutions for the maritime market, but we are by far not limited to that. So when we think about industries, for us, it doesn't actually matter because we find in all of those industries rotating equipment. And maybe you can identify yourself in your environment with either wind power or kind of power related industries, energy production plants, sawmills, for example, in industry where we concentrate as well with a solution to have systems to measure the blades of the sawmill compared to the roller that pull the logs into the machine. Then very typical is processing industry, of course, shipyards as just mentioned, or any kind of manufacturing industry. That's just a few. So to sum up everything, wherever you have equipment, rotating equipment in an industry that in production or on operation depends on the availability of these assets, we are typically involved in that with solution to provide to the technician to align the machine. But coming a little bit closer into our today's topic, and I like to start with what is actually reliability. I already mentioned the word reliability, and today many people using it very casual, but did you ever think about what really reliability actually means? So when you think about us in maintenance and technician engineers and so far, reliability was introduced into the thinking already more than 40 years ago, and it started with the reactive maintenance. So where you have a problem in a machine and you react as a consequence to fix this problem. So you always react to an event on the machine to repair it, to fix it, to replace it. So that's old-fashioned and not applicable today anymore. Many years ago, then the predictive maintenance came in plan. So we are taking statistics to predict how long the machine is operating, or actually when could it fail, so that the machine would be repaired before it actually fails, so to avoid an unplanned shutdown. But also there are certain things have been learned over the years that this is not working out with the statistics because of one reason, and I will show you that in one of the coming slides as well. People then have moved on more into the condition-based maintenance. That means make decisions about certain actions of maintenance or activity on the machine based on certain parameter of the machine. And that's typically a symptom of noise, of temperature, of vibration that says the machine is maybe not well equipped in the moment. Consequently, I like to bring the machine in better condition. It's kind of a health concept that when I am unwell, I'm going to a doctor, check it out, and take a countermeasure, medicine, or get a certain treatment. And condition-based maintenance is here very similar to that. But then people went even a step further and say, why waiting for a problem to occur and only then react? Why I'm not acting proactive? So basically do everything possible to avoid a potential problem in the machine that would come in the future. Why shouldn't I basically invest my efforts into an asset to eliminate potential problems for the future, and that's called proactive maintenance. Consequently, in this proactive maintenance, a lot of references are used that describe tolerances for certain conditions, and consequently, we have here then a precision maintenance, doing the job more precise, setting up the machine in certain tolerances as required by standards like the ISO or the ANSI, the American standard. And then the last stage was then to really focus with the maintenance strategy on the reliability-centered maintenance. That means make everything possible in combination to apply condition-based maintenance, but not only acting proactive, being precise at the machine. The reliability-centered maintenance is so the latest way of applying towards the machine, which typically has the best outcome or the best overall in, yes, saving money. Saving money means reducing downtime of the machine, avoiding repairs of the machine, and extending the lifetime of an asset so that you take the most of this investment out, and therefore saving money. But what does really reliability mean? I have summed that up here in a very simple sentence. The reliability in the machine world simply means without failure and prevent failures from occurring. So then a machine is reliable. There's actually a longer definition existing that says that a reliable machine would operate without any interruption and without any failure for a certain amount of time. And to assure that certain requirements need to be met, requirements of perfect installation operation, and this comes back to perfectly aligned, perfectly balanced, lubricated, etc. And this is something that actually doesn't start with the asset itself. So reliability thinking starts with the people. So people need to change. People need to adapt to those kind of requirements to have a certain strategy to plan actions and to fulfill this action. So therefore, education is important, and this education helps to change the mindset of the people to concentrate on the machine to prevent or failing instead of repairing the machine. So maintenance is always needed, You always have commissioning, handing over into production, and then maintain the machine, but we are no longer aiming to repair a machine after it is failing. We actually concentrate that the machine is not failing at all, and applying our maintenance activities before it comes to that event. And that is a change of people, especially mindset, education, etc. But it also includes managing resources. So resources are rare today. Reduction of manpower is quite common in industries. Everything becomes automated, but a lot of activities in the maintenance world relies heavily on engineers like you. So we need really to plan to concentrate with all of the resources that are given to be focusing on the reliability matter in regards of the machines or assets. And then we have here reliability centered maintenance, RCA included. We have the FTA, that is the fault tree analysis, so kind of a technology, a statistic applied to calculate a certain prediction of individual assets, when it would be failing, how it is failing, how it can be recognized to have an issue. We have the failure mode effective analysis, FMEA, and all of that comes together in certain preventive maintenance optimizations. So that's all bullet words and concentrations in the maintenance world today that is typically applied to any kind of plant and operation where you have rotating equipment. All of them are typically parts of reliability-centered maintenance. And that's why we're also including alignment strategies, precision alignment to be more correct, to help to extend the lifetime of the machine, to reduce failures of the machine. And when we're looking a little bit into those kind of topics, we expect, all of us kind of expect a lifetime operation of a machine that could look like this graph. So we have here in conditional probability of failure, and we say, well, as longer I'm operating with this machine, as older the machine becomes, as more likely it is that the machine is wearing out. Wearing out means it is a likelihood given that there could be a failure, a bearing is breaking or some other components. So consequently, at the beginning and at the event when the wear out starts, I have my useful lifetime. So the useful life of the machine I can calculate, I can predict, but I can also influence it. So I can actually change and extend the useful lifetime, or through wrong handling of the machine, I can shorten it. So nobody likes to have that. But the whole prediction here is kind of a little bit wrong. Because if you're looking into some research, and that happened in the mid-60s, so many, many years ago, there were studies of two persons, Nolan and Heap, that's their names. They are well known in the condition-based monitoring world, that have studied machine failure pattern. And they have figured out, and it is multiple times confirmed after the 60s, it is still true today, that actually only 11% of the operating machines in the world in our industries failing because of age. So the previous slide gives us a certain expectation of a lifetime and when a machine is wearing out. But only 11% of those machines act in exactly that way. Way more, 89% creating failures during the lifetime. So that's an initial break-in period that is potentially random, or the worst scenario, and the most often happen as well, we see that at the bottom right, is the infant mortality. That means actually 68% of the assets today have a very likelihood to fail at the beginning of this lifetime, not at the end. And the reason is quite simple for that, but we all ask, why could it be happen? It's us human, because we are not perfect. So a completely different study has revealed that the reason that machines failing is also here not the aging, it's only 4%, or something that is wearing out in time. It represents 12%, so basic wear and tear. The reason that machines fail, mostly contributed, here mentioned with 84%, is careless work habits. And this means that the machine has not been produced correctly by the manufacturer outside of certain tolerance, that it has maybe not been transported from the manufacturer to its end destination. It potentially has been loaded on a truck, goes over a rough road, gets shocks, bearing are damaged, or on a train. Then it's lifted on site, maybe wrongly by a crane. I have seen that in the field that somebody put the slip around the shaft of a heavy machine and lifts the machine to put it in place. So of course, the whole weight from the machine block is hanging on the bearings connected to the shaft where the crane is mounted on. So at that point already the machine is very likely pre-damaged purely because of either transportation or putting on site. So that is humans that make mistakes. They are treating the machines in the wrong way, or commission the machine, set up the machine wrong on its place. It includes also the foundation of the machine, that the base where the machine is standing on is not as it is required, not flat, not leveled. A putting machine have a soft foot because something has bent. Consequently, when the machine is handed over newly to operation, it starts already with a pre-damage. So all of these reasons is really engineers, technicians who contribute into the lifetime, reducing the lifetime as a consequence, and therefore we have random occurring failures. And with precision laser alignment, you have some tools, there are many others, not only laser alignment, that help you to put the machine in place in the right way as it is required to certain tolerances. Everything with the aim to have here a reliable operation in the future. And that's where we're having this kind of potential failure curve. So also in the vibration world, this information is quite common to be shown. Vibration world means reliability, thinking about the maintenance strategies, that a machine that has a problem, like a human being, creates symptoms. So if I'm having a headache, I'm feeling unwell, my problem is not the headache. The headache is a symptom. It's caused by something else. So consequently, we have electronics and all kind of data analyzer and technologies today to assess the machine conditions to recognize symptoms, but I'm still having to do a root cause analysis to figure out what actually causes this symptom. Because if we never fix the initial problem that the machine today has, we will find ourselves in 1 or 2 years again at the same point. And when you see the symptoms can be developed between the P and the F, so inside of that range here marked starting at a point number 3, that's where we have the potential failure, towards the functional failure when really something is breaking down. That is where the electronics and the instruments today are be able to catch the symptoms. If it is vibration, ultrasound, or thermography, in that range you basically measure a symptom. And as you can see in the chapter before, between the point number 2 and 3, that's where we recommend end user and technician to apply precision shaft alignment. Because the shaft alignment helps actually to extend the lifetime and avoid this catastrophic failure. So instead of waiting that a problem occurs, why not being proactive and doing at the beginning of the lifetime of the machine everything possible to have a machine that is not having stress, no pressure points on the bearing, no misalignment. And this includes rigging of the machine, grouting, balancing, measuring, and verifying the flatness of the base on the machine, the level, coming to the machine, checking and eliminating softwood, and then it comes to the precision shaft alignment. So there are so many things that can be and should be checked today, and we only need the technology and the mindset, the education to do that. So it is proven that precision, and that means laser shaft alignment, contributes into the reliable condition of the machine and extending lifetime. What is machine alignment? So we talk quite randomly about alignment of machine, and I'm sure you have an idea. And the basic idea, yes, is shaft alignment, but not only alignment. So when we think about in misalignment, we talk about the shafts. So misalignment occurs when the driver's shaft center line of a rotating asset is not co-eccentric with the driver's center line. We are not aligning the coupling. We are aligning the machines physically to each other in favor of that the rotating shafts are in center. And we will later learn that we mounting actually our laser measurement components on the shaft to assess exactly this information. The correction of the machine, then on the other hand, is of course on the feet, where we can really countermeasure and doing some shimming. If you think what kind of misalignment could come or could exist, that is parallel misalignment and angular misalignment, and there are various ways what causes this kind of misalignment. An inaccurate assembly of components, and that could be the key for the coupling, that could be the coupling itself, that could be also the bearing or the fully machine on its base. So there are a lot of parts responsible for inaccurate assembly of components. Even a connecting pipe to a pump can be inaccurate assembled and cause a misalignment. The relative position of components shifting after assembly, so that something has changed compared to the initial setup. We can have a distortion by dynamic forces. Dynamic could mean in a pipeline where you have maybe a different medium with a different temperature that pumps inside and outside of a pump of the equipment. So certain things, because of temperature, start to extend and pushing the machine in a wrong position. Consequently, it becomes also misaligned. So this is kind of often summed up as terminal growth, but it's better to say dynamic influences, because the distortion can come by the growth through a temperature of the machine itself, but also by pipe, by medium inside of the pipe or other components. Then we have the coupling phase, which quite often you would be surprised it's not square to the shaft axis. So it's basically wrongly mounted, maybe a wrong coupling that is not supposed to be or designed for this type of shaft and machine is used. Then softwood, a very, very common problem. So softwood is that the machine should really rest on its foundation without that you are bolting it. So we have mostly two pair of feet, so 4 feet, maybe 6 feet, or even more than that. And without having them bolted down, the machine should rest on the foundation without having a certain gap. So there's no wobbling like in the bar where you have a chair. This is softwood. Because what happens when you are tightening the bolts and having it really bolted down in a frame, in a structure, put in shock fast, then you change the body of the machine. You're putting strain into the machine. You're changing the air gap for a motor that hampers the rotation through the magnetism inside. At the end of the day, you're stressing the bearings, because the rotating shaft always works against any kind of stress. And softwood is a very common problem in the machinery that often is overlooked and not corrected. Consequently, your machine creates stresses on the bearings and the bearings fail. So very often when you ask in maintenance world in regards of machines, what are the components that failing the most? It's not a coupling, it's not the shaft, it is the bearing, because the bearings are the ones that carry the load, that carry all the dynamic effects, and if something is misaligned, the bearings getting damaged. Another one is a change in structure, so that the foundation, the soil maybe beneath the machine is getting weak over time because the machine could be heavy. It could become in time loose. So a loose machine that operates quite often creates resonances, also those kind of things going as a stress into the machine, into the body of the machine, into the bearings, and coming with other symptoms to be measured. And all of this is then again going into the bearings getting damaged, the seals getting damaged, lubricant becomes dirty, so there I have dirt and dust in it. Consequently, my bearings again getting failed. So there are many, many reasons why a machine could be misaligned. Inaccurate foundation, loose balls, loose couplings are just few more. How do we recognize misalignment? So also here a little bit about vibration, but very, very simple. Earlier seal and bearing failure. So when the bearing, which by design is actually created to operate infinitive forever. So bearing by itself does not, becomes faulty. If it's lubricated correctly, a bearing would last forever. But throughout load conditions, start, stop, and misalignment, bearing starts to fail. So earlier seal and bearing failure is a symptom that the machine is potentially not correctly aligned. Excessive heat, also related to stress inside of the bearing throughout the rotating shaft. If something is misalignment, then we have typically here a temperature that is increasing. The machine operates with a less performance. So that could mean also it takes more energy to drive a certain driver or just has a higher play. Typical symptoms for misalignment. Another symptom is, yes, vibration and noise. Already explained it a little bit that a vibration is a symptom of an origin problem, a root cause. Higher power consumption, typically. If I have a strain, if I have pressure in my bearings because of a misalignment, I require more energy to drive those shafts to the nominal speed that I want to have. Consequently, if there's a resistance inside, I require more power. On the other hand, if my machine is perfectly aligned, I can save power consumption. I save money, up to 10% in many cases. So alignment check would be then the ultimate way of recognizing misalignment. But of course, I need to access the machine when it's not operating. So it's very quickly done to put the brackets and the measurement technology on a non-operating shaft and just measure and check the condition. But it is required that the machine is not operating. The alignment check is the best one, but there are many others inside of the operation of the machine that I can take to recognize misalignment. And what kind of parameters should I compare my condition of the alignment? Well, we have tolerances. So here we see a table of the ANSI, American Norm of Standardization, which today is worldwide used to describe the minimum of accuracy level that the shafts to each other need to be aligned in. So we're having here typically in association from a certain tolerance to the speed of the machine, and I have here underlined 2 in red. One's 1,000 to 2,000 and second 2,000 to 3,000 RPM. And an excellent alignment, so no harm to the machine, has an offset, an allowable offset from only 0.03 millimeter. So 300ths of a millimeter is my offset. The angle misalignment is 0.04 millimeter. Acceptable is about the double of this amount. So that's a kind of in between good and bad. The bad one I did not even mention. So everything that is neither excellent or acceptable is not permissible. Means that the machine is misaligned and harms components in the machine when it is operating. So those references are inbuilt. You can activate them on a laser alignment system and just compare the condition of the machine to those references. Are you actually inside of those tolerances? Another way, coming back to very quickly only the vibration, recognize misalignment. So many businesses today using some data analyzer vibration equipment. They are also using an FFT, and quite often you should be able to recognize based on the pattern that is given, so not necessarily on the absolute vibration value, that there's a first order and second order appearing. 1x and 2x are the orders of the running speed of the machine. So a machine that runs with 1500 RPM, first order equivalent to 25 Hertz. 2x is the double, 3x the triple. Very simple, but it refers to the speed of the machine. And if you have there some energy, some peaks in an FFT in the vibration world, we can assume that there's a misalignment. So misalignment, we have here differentiation bonds between parallel and angular misalignment. Now, this material which we are showing you here in this presentation, PT Tiara can share with you. So please reach out to Mr. Rojecki and the team. They can provide you all of this information in a kind of a PDF format. The experts maybe that you have in your company in the vibration world can also deal with those kind of matters. I'm just taking them here in the presentation. You have many ways to recognize a misaligned machine. What are the causes? Improper installation, kind of realized it already. Inadequate thermal compensation. So yes, machines having a thermal growth, we need to know that, we need to measure that if we do not know and compensate for that. Structure-based problems. So everything that comes from the foundation of the machine, flatness, levelness, looseness, resonances, and things like that. And dynamic strain, pipe strain, all kind of things that influence my asset from the outside. And I don't really expect you to answer this right now, but think about what is the number one out of those four, which is the highest contributor into the causes of misalignment? Excuse me. Is it improper installation, thermal growth, structure-based problem, or is it pipe strain? The most common of all four is actually the improper installation. And this goes back again to the engineers that just didn't put the machine correctly in place, not correctly into the references and tolerances we have. Machines are in place misaligned, unfortunately. But with education and with activity, we can do that better. Typical consequences. So what happens if a machine operates that is misaligned? Well, 50% of all of the breaks of rotating equipment, and that means mainly bearings, are caused by misalignment. So when somebody wonders why is my bearing all the time failing, could be misalignment, very likely actually. But altogether, we have increased vibrations. Nobody really wants that. We have sealed leakage. So it looks messy, oil comes out, lubrication, grease comes out, need to be greased in a smaller cycle. It's a typical symptom of misalignment. Bearing wear, so the bearing are wearing out very quickly. We have more activities in regards of the maintenance to maintain the machine, repair the machine. we have shortened the lifetime of the equipment, so the lifetime is not reached and the equipment is failing, need to be replaced. All of these are symptoms or consequences of misalignment. And yes, production losses, because if a machine is not available, it is not available to us, means not reliable. I have an unplanned shutdown. Shutdown means I have a loss of production. That's the highest cost that I could, in a negative way, here have. Alignment of machines, of course, is nothing new. It happened since machine actually exists. And the easiest way, but also the least accurate way of checking the alignment of a machine is a feeling gauge. So with this on the right top, feeler gauge showed tool that somebody puts at the edge of the coupling, and eyeballing it, somebody believes to say it's aligned. Well, you need to have a good eyesight, but even with the best circumstances, the achievement of alignment is here maximum a tenth of a millimeter. And you also measure actually on the coupling. You're not measuring on the shaft. So you're putting the straight edge on the surface on the flange edges of the coupling. That's not what we're really interested in, because we measure the surface on the coupling. But what we really want to know is the shaft. So it's very, very subjective. It's not accurate and doesn't really help us much. Consequently, 40 and 50 years ago, dial gauges came into play. So there are two methods, the rim phase and the reverse method, using two dial gauges rotated on the shaft to assess how much play does the shaft actually has in comparison to the other. So the displacement here is then measured by rotating the shaft. Now, really, I draw my hat. That's a phrase to say I respect those people who master dial gauge alignment. It's very complicated. You need to be experienced. You can do many things wrong, and there are only very standard machines that you really can measure with dial gauge. When you have an extraordinary machine, it becomes very hard. But many people still do it. The accuracy that you can achieve here is 100th in the best scenario. But one disadvantage is you do not have a proof. That means people writing down the result in a handwritten report and provide, this is my evidence. Now that's then a trust relationship that maybe in a service contractor relationship to the customer does not always work out. So then 30 years plus, the laser come into play. Way more accurate, so the laser measures with 1,000th of a millimeter, 1 micron. The electronic does the job for me. The brackets are way better and less influenced by potential problems. And I have a digital proof. That means everything that I measure and align the machine is recorded in the instrument. It's not handwritten. I have a digital protocol and evidence that I can provide to my counterpart, to my customer, that I really have commission the machine, repair the machine, and align it accordingly to tolerances that are required. So that's very common today. And EasyLaser is a company that deals with those kind of instruments to help technician engineers in the world to use laser alignment instrument. And I spoke about that with, very traditional people thinking in Japan and South Korea who prefer the dial gauge alignment. I said, so it's fine. If you find those 2, 3, 5 people in your big petrochemical plant that are still master dial gauge, is perfect for you. And I do not doubt that. But the other 20 people in their maintenance departments who are newer generation, young people, do not have the experience. All of them, they cannot do that, because you need really to learn that. With a laser instrument, everybody can do that. It's very simple how to use it, how to apply it to the machine. So we open basically throughout electronics the availability of align a machine in a more precise way to everyone. Without it, you have a learning curve. So it's way more convenient today to do that with laser instruments. As already said, not only the shaft alignment for us is of concern, it's one part of many. So when we think about the installation of the machine, we start actually with the flatness. The flatness of the base where the machine is standing on has to fulfill certain requirements. So it's a geometric condition where the surface has no or little variation in this one plane. Also, the level is important. Most machine is really designed to operate on a level surface. If it's not in levels, leveled means square to gravity. The lubrication of the machine is not working perfect. The load of the machines on its drive end side and non-drive end side bearings could be changed if the machine is not perfect leveled. So there are really serious effects that I cause into my machine if my base is not leveled. And the design of the machines assumes that the machine is standing on a leveled and flat surface. So also here we have norms, tolerances that actually need to be fulfilled. So we have here recommended levelness and flatness for various machine types. And that's something like 0.8 millimeter per meter in regards of levelness and 0.4 millimeter for flatness. So as large, of course, the whole area, as greater the tolerance. And all of those things can be easily also measured simply with a laser. You have a unit that emits a laser and you have another unit that receives the laser. So when you compare them to each other and move them around on the foundation, you can simply compare this plane to each other. Is it flat and is it leveled? Softfoot, already mentioned earlier, it is often overlooked. So here we have a typical picture. There is a gap between the foot of the machine's surface and the base. Of course, when we are bolting it down, what happens? The machine, yes, is rigid, but the whole body of the machine put strain in it. And this strain is transferred into the bearing. From the bearing into rotating shaft. And if I'm forcing my shaft to rotate, my bearings start to fail in time. The soft foot need to be corrected. It can be easily measured with a laser alignment system. It is really essential that we are correcting soft foot. The rule of the thumb says that everything above 0.05 millimeter, which is the gap that we would measure when we loosen the bolt, that needs to be corrected by shimmy. Otherwise, we have modification of the housing geometry, stress induced into the castings, modifying the bearing loads, the lubrication, position of the seals, all of this get influenced purely by a simple soft foot. And this is not rocket science to correct soft foot. But we need to learn it, we need to be aware of it, to be aware how important it is to correct a soft foot. And also when somebody tries to do a shaft alignment on a machine that has a soft foot, you will not succeed. That's also in the favor of those ones who align machines to correct the soft foot at first. Last in this topic here are those dynamic forces. The thermal growth is one potential cause. So the motor in this example is changing throughout the material density from non-operating to operating state because the temperature is increasing. So increased temperature, my material extends. Consequently, the motor changes its position compared to the pump, which maybe even is a cooling water pump. So therefore, we need to understand what are those dynamic forces, because when you align the machine, it's called alignment. And need to compensate for that kind of thermal growth so that when the machine is in operating condition, including in thermal growth, the machine is perfect aligned. The instrument can handle that for you. But you need to know, you need to measure those kind of dynamic stresses to compensate for that kind of growth that you're having here. Another strain could be connected pipes. So this is actually a picture or two pictures from a real case that my colleague in Sweden had. He did some service in Spain, and they basically installed a new gearbox on in pump. So everything needed to be moved away. They fixed the foundation, put a new machine on it, and the flange pipe didn't fit anymore. So very common what people do, they forcing it together. So use some tools and force to put the bolt into these holes to match them. What would happen to the machine? So we bending the whole pipe. This energy goes into the machine, into the asset. We have some pressure points, and consequently here also in misalignment. That misalignment again goes into the same problems as everything we have discussed, or I say to you, our bearings, they take the stress. My machine is misaligned. My machine will be no longer reliable operating. So instead of forcing those two pipe flanges together, the machine or the pipe itself need to be corrected. It need to be aligned so that they are fitting without any force perfectly together. Only then you have a reliable machine installation. So that's all related to thermal expansion and dynamic stresses. Those things can be measured also purely with a laser. So instead of mounting the brackets on the shafts, we just mounting them on the machine to another machine. So we compare the position to each other as a monitoring or recording device. So we operate from the machine cold to hot and see how much the machine is changing in vertical and horizontal axis at the same time. If we once have established that data, we can use this growth or dynamic stress, apply it to the called alignment targets and compensate them therefore. So that means we align the machine always in perspective of the operating and hot operating state. Precision alignment. Also here, try to think simple. Every misalignment goes into the bearing. So here, those two graphics on the right-hand side, we have a rotating shaft in a bearing in the bearing housing. Everything that basically displaces either the shaft or the body of the machine creates stress inside of this bearing. And consequently, my seals get broken, dirt comes inside, I have pressure points in the bearing by rotation the shaft, my bearing starts to get damaged, and sooner or later it will start to have all of those symptoms, vibration, temperature, and then at the end, failing. So rotating machine is a construction with a movement and a driving unit. And the shafts to each other should be aligned in vertical horizontal axis by in range of 0.045 millimeter. We have seen that earlier. And here we have the information about the play of the bearing. So a bearing that has a play from a range of 0.003 to 0.007 millimeter, you can imagine what a certain misalignment does to this play of the bearing. It creates stresses and hampers and damages the bearing. Perfect aligned machine can reduce resistance inside of the machine. Consequently, I do require less energy to drive the shafts. So they have really the ability to reduce energy. You save energy throughout precision shaft alignment. In many cases, 10% and more. And that can be a lot if you have various machines in your assets, in your environment. Cost savings. So there are a lot of things for us to consider why precision alignment is good besides reliability and lifetime. We have 10% power consumption as a potential. We have a reduction typically associated with the bearing, with the seals, with the maintenance of the machine, and we increase the lifetime. So there are really benefits where you save money through a reliable installation and reliable alignment of the machine, precision alignment to be more correct. Just to recap, what is shaft alignment? Shafts are aligned when their rotational center lines are collinear to each other under operating under normal conditions. They would be misaligned if we have either an offset, so we see here parallel misalignment, also called offset misalignment, or angular misalignment. So angular is actually the more harmful one for the machine. But in the practice, the most machines having both in combination, parallel and angular misalignment. That means I need to identify that and doing the correction on the drive side and non-drive side of the feet of the machines that I can move in a slightly different amount to also correct angular misalignment. Benefits of precision machine shaft alignment or alignment general. Increased lifetime from the operation of the machine, reducing costs for spare parts, bearings, seals, reducing maintenance labor. So you focus with your maintenance resources actually to maintain the machine, not to repair the machine any longer. You reduce costs on brackets, on documentation issues. That's in comparison to the dial gauge. You have an improper planned operation and reliability operation as a consequence. The machines, the assets are more available to you for your processes in your plans. You can reduce the power consumption very easily. Consequently also, and it's in all of our interest, you would improve the plant safety, which is in all of our favor. And you can contribute with all of those topics to a more clean environment by reducing spare parts, reducing energy consumption, and so on. There are a lot of benefits. And to achieve all of that, to sum up, we can do something, and we should, in regards of the foundation's flatness and levelness. Then we have the dynamic stresses, which is pipe strain and thermal growth. And on the machine itself, we have the deals of soft foot and of course the shaft alignment. All of this is something with an ordinary laser alignment system can be measured and of course need to be corrected. So the best tool is not doing the correction for you. So engineers and technician maintenance personnel has the tools on hands, assess the conditions of the machine and correcting it also. That is still an engineering discipline. Now, let's talk about vertical orientated machines. It's quite common to have them, and in a way, I must say, kind of a little bit ordinary. Ordinary when I'm thinking about last week maritime, where we think about rubber alignment, stern tube alignment, compressor, gearbox, and things like that. But there are many pumps and other machines that are orientated in a vertical position. Here's a small case. The case is a couple of years old and actually done by an older generation, by an engineer with an instrument of an older generation of easy laser gear. So that's Sundstrand in vertical pump application in Sweden. And they wanted to install the machine, the pump, and align it to the flange without having the motor on the whole framework. So the challenge was here how to align that even without a machine. So you have at the pump at the bottom and at the top where the machine, the motor needs to be mounted, and we're just dealing with the flange. And we found a way with a customized bracket to do that. So just let me go through those 2-3 slides. The first, what the engineers has figured out is we're using a 3-armed bracket. So this is basically our representation of the motor that does not exist yet. And we're putting it at the top of the frame structure where the motor actually would be sitting on. So we have here set up from the first and the second arm where we are measuring the diameter of the flange of the theoretical motor and copy those kind of radius towards the arms number 2 and 3. Then we're putting the bracket on and we're using the third arm, which is a spring-loaded ways to clamp it inside of the flange from the frame structure. And this is to make sure that the whole center part is really in the final center position where also the motor's shaft would be. So you see then in the center in the circle, there's a point or in bold sticking out, which represents at the end the shaft of the motor that we do not have yet. So the challenge is basically to put this whole adapter, the three-legged mounting part, in position to be centered. We see here on the point number 3 on the right hand side the mounting measurement of the top of the frame where the motor would have been sitting, and beneath is actually the bracket on that little kind of bolt that represents our shaft at the end. So the bracket is then mounted, circular, rotated, tested, and there is the measurement unit placed on. So then I'm targeting both measurement units to each other. I put one unit at the bottom on the machine pointing upwards around the shaft from the pump. And the top one represents basically the circle-mounted detector or measurement unit of the flange bracket, which is the representation of the motor shaft. So then I turn on my instrument, and I will do that in another test here live for you just to see how it looks like. I have an X and Y, and I can target my laser perfectly into the center of the detector. So that's my fine adjustment. And then I'm just rotating into 3 final positions, something like 9, 12, and 6 o'clock position, to measure in those 3 positions to each other. So we have 90 degrees in between to assess the condition 3-dimensional of the measurement units, which represent by right the shafts of both machines. Then I get my condition, how the condition to each other of those 2 machines or shafts is look like, and I can do my correction. So here in point number 5, we see those 3 indicated arrows in red. That's my decision points that I declare as number 9 o'clock, 12 o'clock, and 3 o'clock. We do that with clock positions because the measurement units would be able to measure the angular position in a horizontal shaft alignment. So whenever you use those measurement units for horizontal machines and you rotate, the measurement unit know exactly with a 1/10 of an accuracy the angle. Like 12 o'clock is 0 degrees, 90 degrees, etc. But if you are putting the whole measurement units in a vertical position, that means we are relying on the gravity. Then if you rotate, we do not have this angle information anymore. So the electronic does not work because the gravity in all of those 3 measurement locations is the same. Consequently, we as the engineers define our fixed points. They just need to be orientated potentially at the flange bolts or need to be 90 degrees apart from each other. That is good enough. And maybe you make some markings on them, on the objects, to just put and rotate the measurement units into those 3 positions, take a measurement, and then the algorithm of the measurement system comes into the place to calculate everything to each other. So we have here basically the principle of clock position, but in a vertical orientation, like 12 o'clock, 3, 6, and 9 o'clock. They can, but don't have to, be the flange bore. So you can have more bore holes for that, more correction points. When you're doing the vertical alignment in the correction, you're typically using shimming around the bored holes where the motor or the pump is mounted on. So there you change the angle in vertical and in horizontal, or in two different axes to each other. So since 3 measurement points, 90 degrees is actually sufficient enough for the mathematics to work. We also do not require to measure more. If you have done in laser alignment in horizontal, I often recommend the end user to measure maybe 4 or 5 readings. That can be a little bit better in regards of play and backlash on the coupling, effects like that, to take a couple of more readings because they are done very quickly. Since we measure vertically here without the coupling, I don't have a play, I can stick to the minimum of the requirement. It means I can or should measure only 3 points. 3 points, they need to be to each other 90 degrees apart from each other, and that's good enough. So when we have the result, have all of the data, the algorithm, the mathematics in the system is then telling us in those two axes. One's the axis 9 to 3, and second the axis 6 to 12, like a cross, where we are shimming the machine. So we're changing the angularity of one machine in favor to be aligned to the other machine. So the corrections in those angular positions should start at one position to fix it, to finish it, and then you move on to the second. So I recommend to start from the 9 to 3 o'clock. And this can be done with live readings. I will show you that maybe on the camera. And the other axis would be the 6 to 12. So you are the one that defines where is 9 to 3 and 12 to 6. Then we have two axes, and we just following the recommendations or the requirements actually on the instrument to do the correction through shimming on the flange side of the machine boards. All of this can be very easily measured and applied live on the instrument together with the machine correction. And I do that quickly here in an example with the XT app. So the XT that I'm using is in 770. That's just the name of the whole system. And it looks like this. We have some brackets, chain brackets, V brackets, magnet brackets. We have the two measurement units, and we have a display. So the display is an app-based. You can run it actually on your phone, on your tablet, Android or iOS-based, or on our provided industrial grade display unit. But that's just the interface where we are seeing everything and key in some information. So everything is live streamed through Bluetooth connection between the display unit and the measurement unit. And as just said, it's one app for all kind of application that we are supporting with the XT family. So you can, together with also PT Tiara, explore what kind of other features we have. So vertical, like the one that I'm showing you very soon, is just one of many applications that you can cover. This is just the kind of results that you would see on the screen. I have them here on cameras, maybe not the best quality. Therefore, I, being proactive, and have copied from test measurements a couple of things just for us to see how it looks like. So we have a main menu. We choose on this main menu shaft alignment and vertical. We're coming to a screen that requires some dimension. To measure the condition of the machine in regards of alignment, the dimensions are not needed, but to do the calculation for the correction. So how much shimming I need to do, to align the machine, then I need to understand the dimensions of the machine, means the measurement computer needs to understand. So we need to key in the dimensions from the position of the measurement unit. The speed is important for the tolerance, if you remember. Diameter and board, that's then for us to do the shimming. Then we're coming to the menu to simply connect via Bluetooth to the measurement units that are mounted on the machine. Coming to the place where I put my 2 shafts into the position at 9, 12, and 3 o'clock and take the readings. So I take 3 times a reading, then I have my condition of the alignment. I typically would recommend and also do 2 readings just to check, is my first one actually correct? Have I done something wrong? So a little self-check for myself. You come to the results, so I can mix my 2 results. You can pick one of them if you like one more than the other, more accurate maybe. But you can calculate the average of the 2 sequences of readings. You get your live screen of the measurement result. The color indicates red outside of tolerance. The yellow color indicates acceptable, and green means inside of excellent alignment condition, accordingly to the tolerance that you have activated. You do the correction live on the machine. I will show you that very briefly, and then you create your report. You finalize the measurement reading, getting the protocol inside of the instrument. You can send it out via email, or you can just put it into cloud sharing. So that's basically part of the report with all of the data that you once have measured, the dimension that you have keyed in, and everything that you have found the machine with and also left after you correct. So you have a good evidence of your work and how you have left the machine and what kind of condition. That's the part where I say thank you to listen to this presentation and where I'm switching to the camera picture.
Oh, belum.
Mr. Rojecki, are you still there?
Oh yeah, Sven, thank you. We have so many good questions here.
I run a little bit far from the time. I think I have taken too much time.
Okay, we discuss it now or later on?
Maybe you give me 2-3 minutes to show that very quickly.
Okay, no problem.
So you should see right now the camera picture on in rig that I'm having here in front of me. I'm turning on my measurement units. So the rig that I'm using is just vertical, no coupling. The coupling is turned, so they're taken off. I'm using here brackets that are connected with magnets. So I can turn them, of course, independent from each other. I'm starting with one certain position of the measurement units. I'm saying, well, I'm taking actually a template. I created a template. Just give me a second. That includes already the measurements for the dimension of the machine. That makes it a little bit quicker. So you cannot potentially read that, but let me just go ahead quickly because the single data are maybe not so important. So I'm having here a template that is just a machine setup. There I'm having already my dimensions, my 4 boards where I'm doing the shimming or the correction. You can change all those pictures. You can change, of course, the tolerances. So when I'm looking at tolerances in a moment, I have here activated the ANSI standard. So this is what I'm comparing my data to. Here's my speed information. There's my coupling diameter. All of those things are here activated inside of the initial setup. I'm going into the next step where I'm making the communication. One of them is actually off, so they are both connected. I have here multiple hardware that I can connect to. we have now those two measurement units. They are already connected, just that one of them is off. Where is the other one? I think, oh yeah, of course. The lower part, I have closed the lid. I need to open that the laser goes really into the lens. Do you see on the left-hand side that my laser dots hitting the target? We're having here a dual measurement principle, and I'm just rotating basically the two shafts independent from each other. Left, right is in the moment actually not so important. We like to measure the angle, and in favor of also the time, I'm doing that very quickly. I can make an electronic zero, but I keep it as it is in the moment. That's where I like to start to measure in my 9 o'clock position. So I take a reading, number 1. Now I rotate as advised into the second position. Roughly in the center. Take my second reading and my 3 o'clock position. Reading number 3. Now I have already my result. As I said, I would typically measure one more time and mix it, but let's just take this one result. I'm having here a measurement table that my result, my misalignment is listed. If I'm going to the machine view in 3-dimensional, that you can see that we're actually having red on both axes. One's in vertical or horizontal orientation. So one is the 9 to 3 and the other one is the 6 to 12 o'clock axis. When I'm going, just to show you that quickly, into the correction mode, I decide basically where would I like to start. So this is now in the moment my 9 to 3 axis, and I stop at the point number 3. So I'm having here a click on the bottom menu, and I say now doing my live correction. So everything that I would change now here in the condition would basically transmit it live, and you're just shimming as the instrument tells you, but you can also see the live reaction. You already have seen that the color has changed. I try to simulate a little bit to be quickly. To bring basically my machine in a certain range, I will try to bend it a little bit. Then you can see that live on the data that the colors changing. So depend on where I'm putting basically shims, I would now do my correction itself. So this is the way how you would proceed in correcting the vertical alignment of the machine in those two axes purely by shimming on the balls until everything is green. Then you, excuse me, finish the reading, stream it potentially into the cloud. So the instrument has in the background and feature activated that when there's an internet connection, all of the data is going right away into the cloud. That is also for free in the moment for customer. It calls Easy Laser Plus. I have here in this cloud a certain account where all of my data from the instrument I'm using is going into. I'm having here an organization inside of the kind of setup. There I'm having a workspace. In this workspace, I'm getting all kind of pictures that I have in the storage of my measurement unit. And I'm having my reports. So this is a report that I have done yesterday. I have not finished a report on the instrument right now. But in the same way, the whole report would be basically transferred into the cloud. You can invite your customers, you can share it, print it, send it via email from here. You can do that as well with the instrument itself. Okay, so sorry that I have taken so much time.
Okay, thank you, Sven. We have many good questions here. I think more than 15, but some questions already answered.
Okay, you handle them in between.
Yes. Okay, I will start with the first question, yeah, from Pak Edo Widi. Based on your data and your experience, how long should we conduct alignment check for each vertical shaft unit? 1 year, 6 months?
How long means in what kind of cycle?
Yes.
It depends on the operating hours. If you have very new equipment, you can schedule that based on time. But I would advise against it. I would really do that on operating hours. So that starts with newly equipment where you have really a proper alignment at the beginning in evidence to say in 1.5 years, so 18 months. Then you check again, and check again means then in a 12 monthly cycle. If you find in those 12-month cycle any deterioration, then of course the next cycle should come a little earlier. I have one slide that I have not shown in this presentation, but I can share it also with you, Mr. Rojecki, so you can share it with the audience later. That explains a little bit the operating hours for newly commissioned machines or for already in place operating machines based on time interval and based on operating hours. I think it's better to provide you this overview. That is a recommendation from us.
Thank you, Sven. So it's 18 months, yeah?
For
And
newly equipped, for newly
newly
commissioned equipment, under the assumption that this is also checked at the very beginning to be perfect aligned.
Okay, thank you. And we will also share the paper, yeah, to the customers. Okay, and next question from Pak Ahmad Herudin. We have experience for the vertical pump. So in this case is circulating water pump. So suddenly the pump bearing broken, and if we look the vibration trending, the pump condition is in good acceptable condition based on vibration level. But what is the cause of the misalignment for this pump? Is it possible happen suddenly?
It is very hard to tell, of course,
Yeah.
and I know in the experience that many people using vibration on the machines, and then we must need to understand really what does it mean? The vibration looks good inside of the tolerances or not. Are the alarms actually correct? What kind of vibration has been measured? Is it only velocity? Because in velocity, we do not have velocity typically up to 1000 hertz. This does not include bearings. So a bearing that is damaged and makes noise creates actually symptoms for the vibration in a higher range of frequencies, and they should be measured in acceleration. So I would assume that the symptom of a breaking bearing can be measured if it is the correctly measurement instrument and the correct setup, but also the correct cycle. Now, saying that the symptom has not been shown in the vibration side could be a hint that either some of that is wrong or the condition just happened very quickly. To predict and really to assume that it is now a misalignment, maybe it was in resonance, maybe it was a lack of lubrication, a heat problem. There could be so many different reasons. It's basically too far for me in that position right now to tell. Is it a misalignment or could it be something else? So since this bearing is already broken, it's kind of hard to also afterwards to figure that out. I would keep an eye on this machine, but also make sure when it goes back into operation after the bearing has been replaced and the machine is repaired, to make absolutely sure that you measure from the vibration in the right way, that you also have aligned the machine after the repair. And then maybe as a precaution, I would measure quickly with a vibration tool in the correct way every month. If there's no change in the condition and if everything under the tolerances that are set accordingly to the ISO, then you can extend this measurement cycle to do vibration checks. But vibration is typically the best tool to catch the symptom, but it's also not 100%. Because you would have actually a need to measure 24/7 with an online installed vibration sensor to be 100% in a range of controlling the machine. And this is a kind of a conclusion or consideration to invest, to have it there on the machine installed permanently, which costs a little bit more money compared to a portable instrument, where then somebody goes to the machine every 6 months or so. Often it's purely manpower and maybe education that leads to kind of problems. Let's say my machine has failed even though I have a vibration measurement. That means the vibration measurement cycle was not short enough, or the whole instruments was not sufficient, or the setup was maybe not correctly assayed. It is measured velocity from 10 to 1000 hertz, which is not the bearing at all. The bearing have to be measured in a higher frequency in acceleration or in a so-called envelope. So there are now very difficult ways for me to answer that if you can follow me.
Question from Pak Sadudi. We have closed cooling water pump running with little misalignment at the first, and until now the vibration is still low, yeah, and acceptable, around 1 millimeter per second RMS. The question is it safe enough to operate with misalignment while running?
Yes, I would say so. But also here's of course a danger to say that the root mean square. So the vibration value in millimeter per second, which is velocity, it's a very broad one. When you remember on the slide that we quickly had a look at, the symptom of a misalignment is actually that the second order, so the double of the frequency the machine is running with, the double of the running frequency, would be having a symptom of a high peak if the machine is misaligned. Now, if this misalignment exists and no other problem in the machine, and we measure from 10 to 1000 hertz, which is the RMS accordingly to an ISO, it could mean that everything together as calculated overall is for us not really possible to see. So that means the peak is maybe a lot higher than 1 millimeter per second, where your alarm is set. It could be 5 millimeter per second, but everything else around it is so low. Consequently, the average, the RMS value is also very low. So the only real way to figure that is to measure a spectrum on the machine, to really be able to tell where is the amplitude around the first order, second order, and the third order, the running speed of the machine. Because only there you have the symptoms of a misaligned machine.
So I think it need to specify the little misalignment here. Is it acceptable or not? Yeah. what is the value?
Yeah. Yeah, and we can say it's very unlikely that the machine has a misalignment problem, but we cannot rule it out completely. The only way to say, yes, it does not have it for 100% is to do a spectrum analysis on the machine.
Next question from Pak Adinudil. He has two questions. One, the first question, during alignment process with laser, we have to rotate both of shaft. How if we can only rotate one coupling?
One shaft, yeah. That applies to vertical machine or a general machine?
I think general spec.
So the example that I had here on camera, I hope actually that you could see that on the screen sharing. For vertical, I taken out the coupling. That means I rotate my couplings, my shafts independent from each other. Now, if one of the shafts, because of gearbox or whatever reason, is non-rotatable, you just use another bracket. So instead of a V bracket that is fixed with the chain clamped or spanned around the shaft and you need to rotate the shaft, you can use a compromised magnet bracket. So that means you would slide the magnet bracket over a non-rotatable shaft in favor of reposition the measurement unit. And we have actually, for horizontal machines, where we're using then the automatic angle inclination measurement in measurement mode, which calls the pass mode. So you can pass by with one shaft over the other. Basically, you do that in 3 steps. Called uncoupled sweep mode. So this measurement mode is designed for a machine that you would measure with a shaft that is non-rotatable, consequently with a magnet bracket on that side. It's hard to really explain without having a graphic. Maybe Mr. Rojecki, you can get in touch with this person later and I provide you some information how that really looks like. We have a video how this can be made. And this video and pictures can tell a lot better than I'm explaining it purely with words. But magnet sliding on a rotating shaft is the basic answer for the problem when you have a shaft that is non-rotatable.
And Pak Adinudil, second questions, I think same with another question here from Pak Benny. How about if we cannot rotate the coupling manually? Is it need sliding bracket to take the alignment data?
Yeah. Again, the same that would basically do compromise with a magnet bracket, which slides over the whole axis. So the magnet's face is typically axial direction to the flange of the shaft or the coupling, but the whole principle is also that you would take out the coupling so that you really would measure the shafts towards each other. Without having the energy of a potential twist applied to in coupling that forces that together. So we say in compromise that we cannot rotate one shaft, and using there a magnet slider, we should still try to use the other shaft as in the rotating part that achieves typically the best results.
Okay, thank you, Sven. And another questions. Is it our easy laser technology can use to do alignment of vertical shaft? In this case, the shaft there is fixed cover that have the distance 5 centimeters, yeah. And is it possible to do the alignment
where's this distance with 5 centimeter exactly?
Yes, only have the distance 5 centimeters.
The distance from where?
Fixed cover with the shaft, yeah. So vertical shaft, in this case, there is a shaft that only have fixed cover with distance 5 centimeters.
So our measurement units
Yeah.
itself having on the diagonal axis a dimension of about 60 to 70 centimeter. So they are having this kind of cube shape and connected with some brackets, even the smallest bracket, magnet for example, we need to mount those measurement units on the shaft. And consequently, we need, of course, to have a kind of a space around the shaft to be able to rotate of, I estimate quickly, 10 centimeter plus. So if this space is not given because you need to mount the transducer on some way, then you just cannot measure that. But I would need to see a real picture of the machine or a drawing, because in the most cases we find ways to extend with certain brackets, either through in Z bracket to extend it basically into the axial direction, or extend the position of the measurement unit throughout other brackets and posts further away outside of the space limitations that you still can rotate it somehow. So in the most cases, we can find a way, but to really answer you this question, I would need to see that. And maybe there's also something where we can deal with this person a little bit later when we have seen a picture from that machine.
Okay, thank you, Sven. Another question is from Pak Dimas Rinaldi. What are your tips for performing laser alignment if I am currently working on a birds mounted power plant? Are there any specific precautions to take due to the swaying of the birds due to waves? So this is a birds mounted power plant, Sven, on the ship, power plant on the ship.
So
Any
that's
tips?
I'm not sure that I understand the word. So that's on a vessel or on a plant?
Yeah, birds mounted power plant. So like power plant on the ship.
Okay, like an
So
FPSO.
yeah. So what is the tips to performing laser alignment? Because will be due to waves of the sea.
Okay.
Maybe any some precautions
Yeah,
when
so
we do the laser alignment.
when we do the shaft alignment, we purely compare one position versus the other. And when a vessel would change its angle, its position left, right, up and down, because it's on the sea, actually, the movement is for both of those ones the same. That means we can compare in absolute the positioning of the machine to each other completely freely without being worried about how much the whole environment where the machine is located in is potentially changing its position in space. Let's put it in that way. When we look into the potential of a base in flatness is also an absolute measurement. It's always compared to a position where I'm emitting the laser from towards the position where I'm receiving on. So if this is not really bending in a way through certain influence factors, then I can do that quite perfectly. When we think about longer machines, turbines, but also stern tube, then it could be potentially, from temperature or other influence factors, an effect occur that bends my fully asset. That means my laser that I'm using to measure on would be kind of changed its position. But these typical measurements are done not in operation on the vessel. So they are typically done in dry docks when maintenance and things like happen. So for shaft alignment, I think there's no need for any concerns. But when I'm hearing power and things like this, maybe there's an environment consideration that we have in explosion-proof environment. And for that, we have also the equipment as EX or explosion-proof, which is not mentioned here today because it's typically oil and gas, sometimes also power related. We have equipment for that. So it's the same laser instrument, just of a different certification or grade to be explosion proof.
Okay, thank you, Sven. Another
welcome.
question is, how do environmental conditions such as lighting, temperature, fluctuations, and vibration impact the effectiveness and accuracy of laser alignment procedure?
The accuracy is not really changing, but when you use some laser in intense radiated sunlight, it could mean that the detector is no longer be able to differentiate between the laser beam that we are using to emit compared to the sunlight and other radiation. And that can happen when you are really facing with the detector sunlight, and can happen when there's a huge distance between the laser beam and the detector. So we, by specification, can measure on a distance of up to 20 meter. Now, the laser beam in 20 meter by our own specification is strong enough to differentiate on detector with 1 micron. But in that distance, of course, the laser beam is losing potential some energy. And if you do that again over this long distance in sunlight, because a laser beam is nothing different than light, it could be the detector is no longer be able to differentiate. That is quite common to happen with instruments that using a line laser. So the one that I'm having shown you today is a dot laser. That means we can centralize the energy in a slim beam in a dot. They're typically coping with that issue a lot better compared to line laser, where the same energy is shared over a wide range. So typically, in chance to avoid that kind of issue is to shade with a piece of carton with something to protect basically the detector itself from radiated light. So if you have these problems, and I know few cases with a line laser of other products over long distance in open sunlight, that this happened, and they found a solution just by not really covering, but putting a kind of a shadow and shade over the position from the receiving part, to say really that the line laser is not so much influenced on the detector when it hits it by the sunlight. When it comes to vibration, so we have a machine that is out of operation where we are aligning, and maybe the neighbor machines or anything in the process around the hall, the room where the machine is standing on, is creating vibration that goes into the foundation, into the floor, that can of course cause some physical vibration on the machine where I'm measuring. So we always need to keep in mind, we measure with 1 thousandths of a millimeter accuracy. And such kind of vibration can influence, of course, my measurement reading. And what we did in the instrument, you can activate a filter. So that means the filter is based on number settings. As greater the number, as greater the filter becomes. That means it filters away those kind of outside disturbances. And it's especially built for physical vibration that is induced into the machine where you are measuring. So filtering means not actually that we are taking away information. We are not filtering really something out. What the instrument is doing, it measures a multiple time to take just one reading. So instead of 1 or 2, it measures potentially 10 times. And it calculates an average over all of those readings. So if the machine has basically a shaking, and this vibration influenced my laser beam, we would increase the measurement time. We would take more readings and calculate an average. And that is typically good enough to be inside of the required tolerances together with the system and the filter to achieve a very precise measurement reading. The small disadvantage is that with increasing filter, it takes a couple of seconds longer to take the reading. So it's just a matter of seconds for every reading with an increased filter that I require more time. But I think it's a small disadvantage.
Thank you. Thank you, Sven. And the next question is from Pak Budi. He has 3 questions, but I think the second and the third already answered. His first question is, how about when the gearbox and the driver have the distance around 4 meters? How to do alignment with the distance around 4 meters?
Exactly the same way. So the most instruments on the market can either measure up to 3, 5, some up to 10 meter. All of our easy laser instruments can measure up to 20 meter. So it's the same principle, there's no other change, and we don't have really limitations. And the reason for that is that we are using the dual laser principle. So we are sending out from left to the right and right to the left from both measurement units one laser beam to be received on the other end. And this allows us in fair comparison longer distances and angular misalignment to also measure that correctly with the required accuracy and over longer distances. So 4 meters, no problem at all. If you, of course, have in radial gap difference between a cardan shaft, then we have a specific bracket to compensate over that as well. So that's also a shaft alignment that we are using here just with a kind of a different bracket where we compensate by the parallel difference between 2 machine components.
Thank you. Another question is from Pak Irfan. It based on your study case, when that can you show again the study case with the movable device? With the picture show
I still have the screen sharing on.
Yeah, because the question is related to the study case.
I'm just going to the right page. Can you see that?
Yes, next, please. Next slide. This one. The question is for the pump device with the movable device, how to adjust this movable device to adjust.
We typically have a stationary and in movable machine. Easy Laser is one in the world that would allow inside of the program to switch which of those two machines is either movable or stationary. By right, you would basically only correct one machine towards the other. In the most cases, like also in this example, it is actually the bracket that is mounted at the top of the machine. So that means we have here, instead of the motor, put the bracket spring-loaded inside of the circular flange. We have not used the balls where the motor would be sitting. Instead, the whole bracket is basically spanned. Now, the idea is actually that the pump is still not the one that we are correcting. The motor is the one throughout shimming. So the whole exercise, and I maybe have not mentioned that earlier, I'm sorry for that, is to identify the shimming position for the top-mounted motor that we do not have yet, in favor to be aligned with the below-sitting pump. But if you would be able to move the pump in its position, then you can easily switch this arrangement inside of the measurement program to say, I take now the top machine, my bracket or motor as the reference, and adjust the position of the pump. But one of the two machines need to be able to adjust in its position. And depend on the arrangements, you need to decide or can decide on the field application.
Thank you, Sven. I think we have another question, and we will finish. And many questions have the same questions, and already answers. The last two questions is from Pak Iman. Is it can we do the laser alignment with the pump of boiler feed pump? Because the set point of the boiler feed pump not zero. For example, the vertical side of the motors have a set point 0.25 millimeter from the pump, and also in the horizontal side, the pump also have the set point 0.2 from the motor.
Yeah.
So can we do the laser alignment with this condition of the boiler feed pump?
Yeah, so this is basically a compensation factor, likely because of thermal growth. That means those two data that either the manufacturer can give us, which often are not 100% correct, they can be verified and also measured, identified. You just key them in at the initial setting from the shaft alignment. So at the position where you define coupling, motor, machine, your tolerances, you can also key in the compensation factors, like your 0 point. So that means that the machine actually for the cold condition and alignment would be aligned, including that compensation factors. That means actually not perfectly aligned, but when then the machine goes in operating state, this compensation is already there, but the machine works against the compensation. Put it into the theoretical perfect place over the center line of the shafts will be then aligned accordingly to the requirements. So long story again, the compensation factors that you have given or that you have been measured can be keyed in at the initial machine setup. So that is then considered and included in your called alignment to be effective in the hot condition or operating condition of the machine. And you can do that either on the machine feed. So that's where the most manufacturer giving us the data, feed vertical and horizontal throughout jackboards. Or you can use the terminal growth data that somebody maybe has measured, and measured means we are interested in the transfer of power. That means on the shafts. There we measure it, and also there on the coupling you can actually key in the terminal growth or dynamic compensation factors as well.
Thank you. The last question, Sven. In case how this tool's working, if we need to do alignment with some centrifugal multi-stage pump that have floating shaft for axial movement, and also gravitational force maybe also affect the measurements on these tools.
I'm not sure about the last point. Can you repeat this question, please?
The question is if we want to do alignment with some in centrifugal multi-stage pump that have floating shaft for axial movement, and also gravitational force maybe can affect the measurement.
So that's a shaft that would center itself in operating condition through certain hydrodynamic bearing, like a turbine, multi-stage. For those kind of alignment, actually the compensation that we just had earlier, but with a different reason, needs to be known. So how much does really the shaft changes throughout operating condition versus non-operating condition? How much is it sinking or repositioning in one axis? That's something the manufacturer should be able to give us, or we should basically be able to measure that with the same laser instrument that has this feature. Then we know this kind of compensation factor. It's not only throughout in terminal growth or on pipe strain, there could be other reasons like that. The axial play related to also in compensation coupling to compensate this axial play actually wouldn't matter for our consideration, because what we are looking into is purely along the shaft axis, how the radial angle and parallel misalignment look like. From the axial angle, at that point, it doesn't really matter. So it doesn't influence this play. In another scenario, this could be, of course, of interest in squareness and in a bore measurement. If you think about multi-stage poupling, depend on the size, that we can measure here in circular bore in a different way, which is geometric. So we have possibilities to do that with the same equipment, but this is something which you would measure without a shaft. So instead of the shaft, you have the laser beam that shoots basically through the machine and represents the center of the shaft. And we measure then throughout the diaphragms to the support bearings and things like this. What is the positioning to see, are they actually in line? It's a kind of a line or straightness measurement in a closed machine considered to be called bore, and we can do that as well.
Thank you so much, Sven.
Thank you.
Yeah, we have many great questions and also great answer from you. And we have already time to finish the webinar. So many interested questions, yeah. And we should be finished at 3, but now already 3.5.
It's my fault. I'm sorry to
Yeah,
have taken too much time.
Thank you, Sven. Thank
you so
you
much
for joining
everyone.
us. Thank you so much. And for further discussions, further details of the answer, we will follow up with the customers. Thank you, Sven.
Thank you. Have a good day, everyone.
Have a good day. Dan Bapak-Bapak sekalian, jangan leave dulu. Kami minta waktunya sebentar karena kita akan mengundi ya. Berapa pertanyaan? 2 ya? 2 peserta yang akan mendapatkan giveaway berupa e-wallet dari PT Tiara. Semoga cukup ya untuk membeli takjil untuk berbuka puasa. Silakan giveaway-nya di spin. Dan nanti untuk pertanyaan yang belum terjawab secara menyeluruh, nanti boleh mengontak kami, Bapak-Bapak, untuk diskusi lebih detail ya. Karena sangat banyak pertanyaan yang menarik ya untuk didiskusikan lebih lanjut. Oh ya, Sven, sorry, could you please stop the share screen from your side? Thank you. Yeah.
Sorry.
So Sven, we have to give like giveaway to customers who give questions ya.
Yeah, you make a lucky spin. That's
right. Lucky, yes. Lucky draw. Okay, start. Wah, congratulations to Pak Solikin Akbari, the first person who get voucher or e-wallet from PT Tiara.
Congratulations.
And the second winner is, wah, congratulations to Pak Yosep Kriswantoro, the second winner of the giveaway. And the questions from marketing team that Pak Syah Indrawan Ismail, his name is not included ya. Miss ya. Oh, oke. So, nggak ada ya. Jadi Pak Syah, mohon maaf, ini untuk yang bertanya ya Pak ya, giveaway-nya. Oke, mungkin itu saja. Terima kasih Bapak Ibu yang sudah bergabung dalam acara webinar kami siang ini bersama Easy Laser, bersama Mr. Sven Laser. Thank you so much again, Sven, for your time, for your great effort to do presentation and also to do demo.
Most welcome. Thank you for everyone.
Really appreciate with the effort, and terima kasih Bapak Ibu. Sampai ketemu lagi di acara webinar kami selanjutnya. Selamat ngabuburit dan selamat melanjutkan puasa dan sebentar lagi berbuka. Sehat-sehat semua. Salam dari kami PT TRP Brasindo Pratama. Terima kasih banyak.